Section: Introduction. In this section, we discuss recurrent neural networks, or RNNs, which are models that keep a hidden state over time to capture dependencies in sequences. RNNs are particularly useful for tasks like time series analysis and natural language processing, where past information influences current predictions. However, vanilla RNNs face challenges with vanishing and exploding gradients, which hinder their ability to learn long-term dependencies. To address these issues, we have long short-term memory, LSTM, networks. LSTMs are advanced RNNs designed to overcome the vanishing gradient problem, enabling the model to learn long-term dependencies effectively. In an LSTM, we use several components. The input gate controls how much new information is added, the forget gate decides what information to discard, and the output gate determines what information to output. We also use specific functions to scale the outputs, preventing them from becoming too large or too small. An LSTM maintains both a cell state, which holds information over time, and a hidden state, resulting in a total of 4 times the size of the hidden state multiplied by the sum of the input and hidden state sizes in parameters. Section Summary. In this section, we highlight the evolution of recurrent neural networks, RNNs, particularly long short-term memory, LSTM, networks, which address the vanishing gradient problem to learn long-term dependencies in sequential data. We also introduce simplified versions of LSTMs and GRUs, termed min-LSTMs and m-in-GRUs, which can be trained efficiently in parallel and match the performance of modern sequence models while using significantly fewer parameters. Section: GRU. In this section, we introduce the gated recurrent unit, GRU, which simplifies the long short-term memory, LSTM, model by using only 2 gates and a single state, compared to LSTM's 3 gates and 2 states. This reduction in complexity allows for faster training and inference while still performing well on various tasks. We define the candidate hidden state, which suggests a new value for the hidden state. The GRU merges the forget and input gates of the LSTM into one update gate, which determines how much past information to retain and how much new information to incorporate. Additionally, instead of an output gate, we introduce a reset gate that manages how much past information is used to calculate the candidate hidden state. This design cuts down on the number of parameters and computations needed. However, both GRUs and LSTMs still require sequential computation, which means they need to backpropagate gradients through time, leading to linear training time and challenges in scaling to longer contexts. To address this, transformers have become the preferred method for sequence modeling by allowing parallelization during training, although they face their own limitations due to quadratic complexity with sequence length. Recently, new recurrent models have emerged as alternatives to transformers, achieving similar performance while being trainable in parallel and avoiding the backpropagation issues of traditional RNNs. Many of these models utilize the parallel prefix scan algorithm, which efficiently computes prefix operations from sequential data points. We can extend this algorithm to vectors, and we notice that the state recurrences of GRUs and LSTMs align with this vector formulation. In this section, we demonstrate that we can train GRUs and LSTMs using parallel scan by simplifying their gate dependencies. We further enhance these models by removing constraints on output range and ensuring outputs are independent of time. We propose minimal versions of GRUs and LSTMs, referred to as m-in-GRUs and min-LSTMs, which can be trained via parallel scan and perform comparably to transformers and other recent sequence methods. For the minimal GRU, we start by eliminating previous hidden state dependencies from the gates. The original hidden state recurrence can be expressed in a way that resembles the parallel scan formulation. However, since the update gate and candidate hidden state depend on the previous hidden state, we cannot directly apply the parallel scan. To resolve this, we simplify the GRU by removing these dependencies. We adjust the update gate and candidate hidden state calculations so that they no longer rely on the previous hidden state. This allows us to compute all necessary inputs in parallel, enabling efficient computation of the hidden states through the parallel scan method. Section Summary. In this section, we demonstrate that by simplifying GRUs and LSTMs to remove hidden state dependencies, we can enable their training via the parallel scan algorithm, which allows for efficient computation. This leads to the development of minimal versions, min-GRUs and min-LSTMs, that perform comparably to transformers while avoiding the limitations of traditional recurrent networks. Section. Step 2. Drop range restriction of candidate states. In this section, we focus on simplifying the GRU and LSTM models by removing certain restrictions and dependencies. First, we drop the range restriction on candidate states in GRUs. In GRUs, the previous hidden state and the new candidate hidden state combine to maintain a consistent scale. The hyperbolic tangent function limits the range of these states between -1 and 1, which helps stabilize training and prevent vanishing gradients. By eliminating this range restriction, we can further simplify the GRU, leading to a more efficient model, which we call min-GRU. This new model requires significantly fewer parameters and can be trained much faster, achieving a notable speedup in training steps. Next, we address the LSTM model. Similar to GRUs, LSTMs also use the hyperbolic tangent function to restrict their states. We remove this restriction for both the candidate cell state and the hidden state, allowing for a more straightforward computation. Finally, we ensure that the outputs of the LSTM are time-independent in scale. In LSTMs, the forget and input gates can lead to time-dependent outputs, complicating optimization. To resolve this, we normalize these gates so that their sum equals 1, ensuring consistent scaling. We also eliminate the output gate, which scales the hidden state, making the hidden state equal to the cell state. This means we can drop the cell state altogether, simplifying the model further. In summary, we have streamlined both GRU and LSTM models by removing unnecessary restrictions and dependencies, resulting in more efficient architectures. Section Summary. In this section, we simplify GRUs and LSTMs by removing the range restrictions on candidate states and ensuring that outputs are time-independent in scale, resulting in a more efficient model called min-GRU. This model significantly reduces the number of parameters and allows for faster training, achieving a 175 times speedup on AT4 GPU for a sequence length of 512. Section. Min-LSTM. In this section, we present a minimal version of LSTM, referred to as min-LSTM, which is much more efficient. It requires only a small number of parameters compared to the traditional LSTM. Specifically, min-LSTM needs 3 times the product of the hidden size and input size, while LSTM requires 4 times the sum of the hidden size and input size. Additionally, min-LSTM can be trained in parallel, which significantly speeds up the training process. For instance, we observed a speedup of 235 times for sequences of length 512 on AT4 GPU compared to LSTM. In terms of parameter efficiency, min-LSTM uses only 38%, 25%, 19%, or 15% of the parameters of LSTM when the hidden size is a multiple of the input size. We also compare the minimal versions, min-LSTMs and min-GRUs, with their traditional counterparts and modern sequence models. We provide pseudocode, PyTorch implementation, and detailed experimental setup in the appendix. At test time, recurrent sequence models operate sequentially, making their inferences efficient. However, traditional RNNs face challenges during training due to their linear training time, which has led to their decline in use. The renewed interest in recurrent models stems from new architectures that can be trained efficiently in parallel. We focus on comparing the training resources of traditional RNNs, LSTM and GRU, their minimal versions, min-LSTM and min-GRU, and a recent popular model called Mamba. We use a batch size of 64 and vary the sequence length, measuring the total runtime and memory complexity for forward passes, loss computation, and backward passes. Regarding runtime, we find that min-LSTM, min-GRU, and Mamba have similar runtimes for sequences of length 512, averaging around 2.97, 2.72, and 2.71 milliseconds, respectively. For sequences of length 4096, the runtimes are 3.41, 3.25, and 3.15 milliseconds. In contrast, traditional LSTMs and GRUs have runtimes that increase linearly with sequence length. For a sequence length of 512, MN GRUs and MN LSTMs are 175 times and 235 times faster per training step than their traditional counterparts. This speedup becomes even more pronounced for longer sequences, with MN GRUs and MN LSTMs being over 1,300 times faster for sequences of length 4096. In terms of memory usage, MN GRU, MN LSTM, and Mamba require more memory than traditional RNNs due to their larger computational graphs. The minimal versions use about 88% more memory than their traditional counterparts, while Mamba uses 56% more memory than MN GRU. However, runtime is the primary bottleneck in training RNNs. We also discuss the effect of removing the dependency on previous hidden states in MN LSTM and MN GRU. Traditional LSTMs and GRUs use their previous hidden states to compute their gates, allowing them to learn complex functions. In contrast, MN LSTM and MN GRU simplify this by relying only on their current inputs, making their gates time-independent. However, as we stack layers in deep learning, the outputs of the first layer become time-dependent inputs for the next layer, allowing for more complex function modeling. We observe that increasing the number of layers improves performance on tasks like the selective copying task. Additionally, more layers lead to increased stability and reduced variance in accuracy. While both MN LSTM and MN GRU can solve the selective copying task, MN GRU tends to be more stable and consistent, as it manages information flow with a single set of parameters, making it easier to optimize compared to MN LSTM, which uses two sets of parameters. Section Summary. In this section, we present MN LSTM and MN GRU, which are more efficient than traditional LSTMs and GRUs, requiring significantly fewer parameters and enabling parallel training, resulting in up to 1361 times faster training for longer sequences. We also observe that while these minimal models use more memory due to their computational graph, they achieve improved performance and stability, particularly with increased layers, with MN GRU demonstrating greater consistency than MN LSTM. Section. Minimal LSTMs and GRUs perform well. In this section, we examine how minimal LSTMs and GRUs perform. Previously, we demonstrated the efficiency improvements gained by simplifying traditional RNNs. Now, we focus on how these minimal versions of LSTMs and GRUs stack up against various popular sequence models. For the long-range selective copying task from the Mamba paper, we note that this task is more challenging than the original copying task because the input elements are randomly spaced from their outputs. To tackle this, models must remember relevant information and ignore irrelevant tokens. We compare our simplified LSTMs and GRUs, referred to as MN LSTM and MN GRU, with well-known recurrent models that can be trained in parallel, such as S4, H3, Hyena, and Mamba, S6. According to the Mamba paper, only S6 successfully solves this task. However, both MN GRU and MN LSTM also manage to solve the selective copying task, performing similarly to S6 and surpassing all other models. The content-aware gating mechanisms in LSTMs and GRUs make these minimal versions effective for this task, which many popular models struggle with. Next, we look at the Mu-Jo co-locomotion tasks from the D4RL benchmark, specifically in the environments of Half Cheetah, Hopper, and Walker. We train our models on 3 datasets of different quality: medium, medium replay, and medium expert. We compare MN LSTM and MN GRU with various decision transformer variants, including the original decision transformer, decision S4, decision Mamba, and decision RN, using baseline results from the respective papers. Our findings show that min LSTM and M in GRU outperform Decision S4 and perform competitively with Decision Transformer, RN, and Mamba. Unlike other recurrent methods, Decision S4 lacks input-aware transitions, which impacts its performance. Overall, across the 9 datasets, min LSTM and M in GRU exceed all baselines except for Decision Mamba, where the difference is slight. Finally, we address a language modeling task where we train a character-level GPT on Shakespeare's works using the Nano GPT framework. We present learning curves comparing min LSTM and M in GRU with Mamba and Transformers. Our results indicate that M in GRU, min LSTM, Mamba, and Transformers achieve similar test losses of approximately 1.548, 1.555, 1.575, and 1.547, respectively. Mamba, while slightly less effective, trains faster, reaching its peak performance at 400 steps, whereas M in GRU and min LSTM continue training until 575 and 625 steps, respectively. In contrast, Transformers require significantly more training steps, about 2,000, making them slower and more resource-intensive compared to the linear complexity of M in GRU, min LSTM, and Mamba.